Our guest today is Jeff Buzen, and Jeff is a leading figure in developing Q-network modeling algorithms for modeling complex computer systems and networks. And if you're thinking about career in modeling, you definitely have to read his book on rethinking randomness. Jeff has a lot of accomplishments. Some of his students were world-famous Robert Metcalfe, who was a co-inventor of the Ethernet. And the second one is Bill Gates, who was a co-founder of Microsoft. First time I heard about Jeff Buzen when I was working on my PhD dissertation in 1977, and I was reading his famous article on Q-network modeling algorithms, simplifying modeling complex computer systems and networks. I met with Jeff in 1981 when I visited with some of my colleagues BGS Systems, company co-founded by Jeff, and the company was in Boston. At that time, we learned how to install and use best one MVS to model computer systems. Later, I used some of his results and algorithms when I was teaching graduate courses at DePaul University in Chicago and was working on developing software, performance prediction software for modeling complex multi-tier distributed parallel processing systems. I really appreciate our friendship and the opportunity to ask Jeff several questions. Jeff, thanks for joining us, and I have a couple of questions for you. So,
okay.
I know my first question is, how do model fit in decision-making process?
Okay, well, the first point is that people are always making decisions all the time, and there's uncertainty involved in many decisions. And what models really do is they help you make better decisions. They basically allow you to identify solutions or alternatives that are not particularly likely to be good and to find the good ones. And they don't really have to be perfect to do that. All they really have to do is reduce the level of uncertainty to help you focus in on which decisions are the most promising or which alternatives are the most promising. And so I view models as a way to support your thinking when you're looking at alternatives.
Yeah.
Okay.
Yeah. Thanks. And when we use modeling, there are really different options. Can we trust models?
That's a fair question, and certainly there have been some examples just recently of models that have not proven successful in predicting various things. So once again, models are usually not perfect. The real issue is can you get something useful from a model? And if the model is giving you results that are not accurate, that are just wildly off, they're not successful. So how do you identify the successful models? There are a few things you can do. One of the things that you can do is do a series of validation experiments where you compare model predictions with actual observations over a period of time, but then you're not really sure that they're also going to work well in the future. So you really want to look a little more carefully at the structure of models. The thing that a lot of people don't understand is that the same model can produce a family of predictions, some of which are very solid and some of which are very risky. And the problem that you run into is if you compare the model with a series of observations, you may only be looking at the non-risky cases, and then when you go off into the future, you're into a much higher risk case. So the models are less trustworthy, less robust. And the point of the work I've been doing recently is to try to identify which predictions are risky and which predictions are less risky for a given model. It's not usually thought about, but the interesting observation is that some modeling predictions are high risk, some are low risk, even though they all come from exactly the same model. And that's the research that I've been doing recently, and that's what I talked about at CMG this past week at the conference here in San Diego.
So modeling results provide some sort of expectations,
Mm-hmm.
okay, which reduce uncertainty, risk surprises, and then by comparing actual results with modeling, we can find is the model accurate or not. Is it right?
Yes,
Okay.
that's one of the steps.
Okay. Okay.
But then when you want to use the model for the future,
Right.
to answer the kind of what-if questions that are at kind of the heart of modeling, the issue is, are you pushing the assumptions of the model too hard? Are you trying to go beyond the standard level of reliability of a model? And that's where you have to kind of rethink the kind of foundations that the model is built on. And that's the kind of work that I've been most interested in recently. And it's something that most, even mathematicians don't understand. They figure that you analyze a model, you get a set of predictions, and they're all equally reliable, and assuming that they've been derived accurately with no errors. And the point is that even if they're accurately derived and there are no errors, there is a chance, or there's a likelihood, that some will be more reliable than others. And in the case of, say, computer performance, I've discovered that predictions of things like the 90th percentile of response time are higher risk than predicting the chances that queue length will exceed a certain limit. So when you're worried about service level agreements, you want to be aware of these things to come up with service level agreements that are more likely to be satisfied in practice.
So can we make good decisions, not necessarily optimal decisions, good decisions without high accuracy and confidence in our modeling results?
Well, then again, you know, you're always making decisions. So the real test is the quality of the decision that you make without a model versus the quality of the decision that you make with a model. Mm-hmm. So yeah, I think models can quite often improve the quality of your decisions, mm-hmm. even if they're not perfect.
Okay. So this is then another probably logical question. If somebody would like to be participating in developing models and using models, what kind of skills people need in order to successfully build and use models to justify business or IT decisions?
Yeah, that's an interesting question. I mean, there are people who study sort of the mathematical properties of models, and they're very good at deriving solutions, but that's not really the essential skill. The essential skill is to understand the main factors that influence the performance of the system that you're modeling. And the big problem is that there are so many factors usually available that you have to zero in on the ones that are having the heaviest impact and be willing to ignore or not represent in as much detail those factors that are less influential. And sorting them out is a big challenge. I always like to take the point of view of say a transaction flowing through a system, and that can be a computer transaction flowing through a system, or it can be something going on in a bank, or you can, when you go to the supermarket and you buy groceries and you check out at the checkout counter, you are that transaction. So in all cases, you really understand what's the life cycle of the transaction? What does it look like from the time it arrives to the time its work is completed? What does it need to do? What services does it require? And to me, that's the best way to start building any model, to understand how the system really works at the basic level.
Okay? And if somebody's starting, what kind of background they need, what kind of things they have to learn in order to be successful in modeling?
Well, if you're going to be doing mathematical modeling, you need a background in mathematics. But again, mathematics is not the same as modeling. Mathematics is a skill you need. On the other hand, it's perfectly valid to evaluate a model through simulation. So in that case, programming languages that have to do with simulation are the things you have to be able to be a master of to do that. But that's only that's only part of the problem. The big issue is to really dive in and understand how a system operates. What are the main forces that control the performance or the activity or the behavior of a system? And how do these factors influence the behavior or the activity of the transactions that are flowing through? So I always think, again, take the point of view of a transaction and just look around as you go through the system and think about what resources you encounter, what delays you experience, what quality of service you receive as you progress through whatever system it is that's being modeled. So that's the kind of, I call that systems thinking. And that's different from mathematical thinking, or it's different from programming, but it's what you really need to build a successful model.
Great.
Okay.
Jeff, thank you very much for sharing with us your ideas, thoughts about modeling and what should be done in order to become a successful modeler.
Okay,
Thank
it's
you
a
very much.
pleasure.
Thank you.
Very good.